So let's try a sample problem and see if we can figure out which of the various equations would be useful for here. Let's just kind of look at what information is given. 3 liters, I know I see that unit liters means it's a volume of hydrogen at negative 20 degrees Celsius. Again, these units help identify this as a temperature. I will need to convert to Kelvin. Are allowed to warm to a new room temperature of 27 degrees Celsius, so I have a second temperature. What is the new volume? Well, again, that would be a second volume if the pressure remains constant. So we have V1, V2 is what we're looking for, T1, T2. So when I look at my formulas, I could either use my combined gas law and then cross out the pressures because the pressure remains constant, or I can recognize this is Charles's law. Oops, V1 over T1 equals V2 over T2. This should be a 1. I am going to have to convert my temperatures to Kelvin. So we have T2 would be T1 is negative 20 plus 273, and that's 253. T2 is 27 plus 273, and that's 300 K. So now we can plug in our variables. So we have 3 liters over 253 K is equal to question mark, or we could leave it as V, whatever variable you choose, over 300 K. So to solve for my unknown variable, maybe we should leave that as V2. I need to get rid of the 300K. In algebra, we know that we can get rid of that by multiplying both sides by 300K. Note that the units of Kelvin will cancel, and V2 is going to be equal to 300 times 3 liters divided by 253, which is 3.55. I'm going to round that to 3.6 liters. Also, we should always kind of do a general check. So in this case, if the temperature increases, we know that the temperature and volume are directly proportional, so the volume should increase. And it started at 3 liters, and it ended at 3.6 liters, so it did increase. So this seems like a reasonable answer. Okay, under constant pressure conditions, a sample of hydrogen gas initially at 88 degrees Celsius and 9.6 liters. Note that this is a degrees Celsius, that's temperature, and 9.6 liters, that's a volume, is cooled until the final volume is 3.4 liters. So note this is a second volume, and they want to know what is the final temperature. That would be a second temperature. So hopefully we recognize this is Charles. If I don't, I could always have started with the combined gas law. But recognize that since it's constant pressure, the first pressure and the second pressure are the same value, and therefore they cancel. And I would basically have rederived Charles's law. So I have my volume 1 is 9.6 liters. Volume 2 is 3.4 liters. Temperature 1 is 88 plus 273, which is 361 Kelvin. Plugging in, I have 9.6 liters over 361 Kelvin is equal to 3.4 liters over my second temperature. Note that the variable I want is on the bottom of a fraction, and this always can present a little bit of problem algebraically. Most people find that the easiest way to deal with this algebraically is to we need to get the temperature, the variable, out of the bottom, and the easiest way is to kind of cross multiply and come up with an equivalent algebraic relationship. 9.6 liters times T2 is equal to 3.4 liters times 361 Kelvin. Again, now that I want to isolate this, I can divide both sides by 9.6 liters. And on this side they cancel. T2 would then be 127.8, whoops, that shouldn't be it's 127.8 Kelvin. We would probably round that to 128 Kelvin. And just as a check, this is the volume, relating volume and temperature, and I know that if the volume is decreasing, it is directly proportional to temperature, so that the temperature should be decreasing as well. And it's gone from 361 to 128 Kelvin, so that is reasonable. 725 milliliters of a gas at 0.970 atmospheres is allowed to expand at constant temperature until its pressure becomes 0.541 atmospheres. What is its final volume? So milliliters is a unit of volume, and atmospheres is a unit of pressure. And it's allowed to expand at constant temperature, so I know that this is going to be a Boyle's law problem. Temperature won't be involved until its pressure becomes 0.541 atmospheres. Here's another pressure. What is its final volume? So note that it's asking for V2. So this is a P1 V1 equals P2 V2 problem. And I'm going to plug in my variables. 0.970 atmospheres times 725 milliliters is equal to 0.541 atmospheres V2. I'm going to divide both sides by 0.541 atmospheres. Have to do it to both sides of the equation, so I divide this side by 0.541 atmospheres. My atmosphere units will cancel, and V2 is equal to 0.970 times 725 divided by 0.541 for 1,299.9, which rounds to 1,300 milliliters. Technically, if I'm going to be correct on sig figs, this should be a 3 sig fig answer, which means it should be 1.30 times 10 to the third, so that I make sure that last zero is not seen as being significant. Okay, so if I want to do a check on this, the pressure decreased in this case, and I know that pressure and volume are indirectly proportional, so the volume should be increasing. And it went from 725 to 1,300, which is an increase, so this is a reasonable answer. The pressure of 6 liters of a gas at STP is decreased to 1/3 of its original pressure, and its absolute temperature is decreased by 1/2. What is the final volume of this gas? So I have a V1, and I have a T1 and a P1. My first temperature and first pressure are the standard pressure. Temperature would be 273 Kelvin, pressure would be 1 atmosphere, and it's decreased to 1/3 of its original pressure. So I know that pressure 2 is 1/3 of pressure 1, and I know that 1/3 of pressure 1 is 1 atmosphere, so it's really going to be 0.333 atmospheres. And its absolute temperature is decreased by 1/2, so that means that the second temperature is 1/2 of the first temperature. What is the final volume of the gas? I'm kind of corralling all our variables. V1 is 6 liters. T1 is 273 Kelvin. P1 is 1 atmosphere. T2 is 1/2 of 273, which is 136.5 Kelvin. And P2 is 1/3 of P1, which is 0.333 atmospheres. Okay, and I'm looking for V2. So let's find this is going to be a combined gas law. I don't have anything constant. P1 V1 over T1 equals P2 V2 over T2. And substituting in, I have 1 atmosphere times 6 liters divided by 273 Kelvin is equal to 0.333 atmospheres times V2 over 136.5 Kelvin. And I need to multiply both sides by 136.5 Kelvin so that it will cancel on the right. And I need to divide both sides by 0.333 atmospheres so it'll cancel on the right. Have to do it to both sides. Note that my atmospheres and Kelvin units are going to cancel. And I'm going to be left with V2 is equal to 136.5 times 6 liters divided by 0.333 times 273, which rounds out to be 9 liters. I can't really do a proportionality check on this one because I have 3 variables going on. I have temperature is decreasing, which would tend to make the volume decrease, and I have pressure decreasing, which would tend to make the volume increase. And so the only way to really do it is with math. But this is a reasonable answer. So a manometer is one of our pressure measuring devices, and it's one that really relies on us being able to compare what's happening on 2 sides of a liquid-filled tube. So it's a U-shaped tube filled with liquid. Typically the liquid is mercury, but sometimes it's water. And we can compare the pressure of the 2 different gases. So if I know what the pressure is of either side, the air side or the gas side, then I can measure the pressure of the other side. Both gases are pressing down on the liquid on their side of the U. So in an open manometer, one side is open to air and the pressure is to the other side is compared to that air pressure. So that's typically how we work it, is we measure the pressure in the air in the room and we leave one side open, and that becomes our reference side, and we can compare it. So looking at the manometer, we see 3 different scenarios. In the left scenario, the gas pressure side has a lower liquid level on its side of the tube than on the air pressure. That tells us that it is higher in pressure on that side. So the gas pressure is higher than the air pressure. In the middle diagram, we see that the 2 sides have equal heights. That's telling us that they're both pressing equally hard onto that liquid and that the pressures are equal. On the right side picture, we see that the gas side is much higher. The liquid is much higher on the gas side than on the air side. That means that the air pressure is higher than the gas pressure. If the gas pressure is higher than the air pressure, we would add the height difference. That height difference is telling us the difference in pressure. How different in height those 2 sides are is the difference in pressure. So we would add that height difference. If the gas pressure was lower than the air pressure, we would subtract the height difference. So let's suppose that this was water. I'm looking at this being centimeters and it's not showing up, but the water pressure, let's assume that this liquid is water. So these units of pressure would be centimeters of water. So in this case, on the left-hand side, the high side is about 1,390 and the low side is about 590. It's a little difficult to tell in these pictures, but if I subtracted those, that's 800 centimeters of water difference in pressure. So if I had a starting air pressure of 1,100 centimeters of water, and I add that 800 difference, that makes 1,900 centimeters of water. On the right-hand side, if the height on the left side is 1,400 and the height on the right side is 550, that's a difference of 850 centimeters of water. Again, if the air pressure was 1,100 centimeters of water, then I would subtract that 850 to say, in this case, the gas pressure is 200 centimeters of water. And there it goes, finally popping up. So if the blue liquid was water and we measured the air pressure and it was 1,100 centimeters of water, that was how we would go about reading this manometer. So note that we're going to often have to convert pressure. Um, Many times we'll measure pressure with different devices, which will give us different units. But when we have to make conversion, we'll have to add or compare pressures. They need to be in the same units. So we've done this before with lots of other conversions. So it's important to know our equalities, that 1 atmosphere is 760 millimeters of mercury. Also, another name for 1 millimeter of mercury is called a torr, so it's also equal to 760 torr. That's equal to 10,332 millimeters of water, or 1,033.2 centimeters of water. So if the liquid was mercury, I would use the millimeters of mercury setting. If the liquid was water, I would use probably centimeters of water. Note that these sizes are much different. Mercury does not change very much with pressure, and that's why we typically use mercury. It's a nice device, nice substance to use. And any of these, we're going to start with whatever our starting conversion, whatever our starting number is. We've measured the pressure in millimeters of mercury, so that would be 1570 millimeters of mercury. If I wanted to convert it to atmospheres, then I would put the desired units on the top and the units that I'm trying to convert on the bottom so that they would cancel, and I could convert my answers. It is important to note that you have to be, when you see millimeters of mercury or centimeters of water, you can't treat that as a distance unit. You can't just convert from centimeters to inches or from centimeters. These are pressure units. When we're talking about centimeters of water, we're now not talking about a distance, we're talking about a pressure. And that can be a little bit confusing.